Welcome to this lesson on linear programming. So far in this series, we've seen that linear programming is a process used to find the best possible solution to a problem within certain limitations or constraints. We've seen that we can work out what the constraints to the problem are and write them as linear inequalities, and then plot these inequalities on a set of axes. This defines the boundaries of the feasible region, the area where the possible solutions are grouped together. We can then test every point in the feasible region to work out which one is the best solution. In this lesson, we're going to extend the work we've done so far by working out another way to find the best or optimal solution from a range of possible solutions. By the end of this lesson, you should be able to find the optimal solution by testing the points in the feasible region and use a search line to find the optimal solution. We'll start with a problem that we've worked with in a previous lesson. If you remember, we wanted to work out the best mix of two products for a patient who needed a nutritional supplement. Each serving of the mixture needs to have at least 20 units of carbohydrates, 18 units of protein, and 12 units of fat in it. We used X and Y for the number of scoops of each product. Each scoop of Max Health has 2 units of carbohydrates in it, and each scoop of NutriFood has 4 units of carbohydrates in it. So we could set up a linear inequality for the amount of carbohydrates in the mixture. 2x plus 4y must be greater than or equal to 20. If we do the same for protein, we are given that each scoop of Max Health has 1 unit of protein in it, and each scoop of NutriFood has 6 units of protein in it. So, x plus 6y must be greater than or equal to 18. Then if we look at fats, we are given that each scoop of Max Health has 4 units of fat in it, and each scoop of NutriFood has 1 unit of fat in it. So 4x plus y must be greater than or equal to 12. We can represent these 3 linear inequalities with graphs. By now you should be able to plot these graphs quite easily. This is what we get. This straight line graph is for 2x plus 4y equals 20. The line divides the graph into 2 sets of points, points below the line and points above the line. One of these sets of points will satisfy the inequality while the other won't. So we need to decide which side of the line to shade to show the inequality. I can choose a point and test it to see if it satisfies the inequality or not. Look at this point, 1, 3. The x value is 1 and the y value is 3. If I substitute this into the equation, I get 2 times 1 plus 4 times 3. That's 2 plus 12, and that's equal to 14. 14 is clearly less than 20, so this point doesn't satisfy the inequality. That means it can't be in the feasible region. Now you should check another point on the other side of the line just to confirm that you're right. I will leave that to you to do. Any point you choose on the other side of the line should satisfy the inequality. So I can shade the side of the line that shows that none of the points satisfy the carbohydrate constraint. That's this side. We shade this side so that we don't clutter up the feasible region. The graph for the protein constraint looks like this. And again, we've shaded the side that doesn't satisfy the inequality. Here's the graph to represent the fats constraint. If you compare this to what we did on a grid of points, you'll see that the shape of the feasible region is the same. Have a look at the three graphs together. The clear part here is the feasible region. However, we don't need to consider every single point in the feasible region. For example, look at this point, 5.5, 3.5. It's in the region, but we don't need to consider it because we aren't working with fractions of a scoop in this problem. So, we only need to consider the points that represent combinations of whole scoops of the two products. On the graph, that is whole numbers for the x and y values. Now we are ready to find the optimal solution, that is, the best of all the possible solutions in the feasible region. In this nutrition problem, we want a mix of Max Health and NutriFood that will give us the right amount of carbohydrates, protein, and fat. The other part of the problem is to find a mix that is as cheap as possible. The patient wants to spend as little money as possible. So let's look at what these two products cost. Max Health costs 10 cents a scoop and NutriFood costs 30 cents a scoop. Now we can test some points in the feasible region. How about this point, 6, 5? This point represents a combination of 6 scoops of Max Health and 5 scoops of NutriFood. At this point, the cost will be 6 times 10 plus 5 times 30, that's 60 plus 150, which is 210 cents. That's 2 rand and 10 cents. Let's choose another point, 3, 7. That's 3 scoops of Max Health and 7 scoops of NutriFood. 3 times 10 plus 7 times 30 comes to 240 cents. If we continue testing each point, you should start to see a pattern in the values that we are finding. Do you see that several points have the same cost value? Can you see which point works out to be the cheapest? The cheapest solution to the diet problem is this one here at 6.2. A mix of 6 scoops of Max Health and 2 scoops of NutriFood will meet all the constraints, so it's in the feasible region. It also costs the least at 120 cents or 1 rand 20. For one serving of the supplement, this seems quite reasonable. Remember that the patient probably needs a serving every day. Let's look at how we found our answer to this problem again. We found linear inequalities for each constraint to the problem. Then we plotted these on a set of axes to find the feasible region. After that, we tested points in the feasible region until we found the point that worked out to the cheapest cost. Now we need to see if there's a quicker way to find the optimal solution without testing every point in the feasible region. Look at the graphs. Do you see that there are some points that work out to exactly the same cost of the mixture? Look at these points. They all work out to a cost of 210 cents. Look at these points. If I join them, you can see that they lie on a straight line. Now do you see all the points that have a cost of 200 cents? They also lie on a straight line. Here are all the points that have a cost of 190 cents. they can be put on a line too. The solutions with the same cost values all lie on a straight line. And what's more, the lines that we have drawn here are all parallel to each other. These lines represent groups of possible solutions to the problem. The lines represent the cost of the mixture at different possible points, and they all have the same gradient. We can write an equation for the cost of the mixture of Max Health and Nutri-Food. The cost of the mixture is equal to the cost of Max Health and the cost of Nutri-Food. If I use X for the number of scoops of Max Health, and each scoop costs 10 cents, that comes to 10x. If I use Y for the number of scoops of Nutri-Food, and each scoop costs 30 cents, that comes to 30y. So I can say the cost is 10 times x plus 30 times y. I can write this equation in the form y equals m times x plus c. To get y on its own, I can subtract 10 times x from both sides. If I write down the equation starting with 30 times y, I'll get 30 times y equals negative 10 times x plus cost. Let's use a capital C for cost. Next, we need to get the y by itself, so let's divide both sides of the equation by 30. That gives y equals negative 10 divided by 30 times x plus cost divided by 30. And you can simplify that to give y equals negative 1/3 x plus c divided by 30. So we have the equation for a straight line with a gradient of negative 1/3 and a y-intercept of c divided by 30. Let's see if that's the same as what we found on the graph. Here's the line that joined the points with a cost of 210 cents. We can work out the gradient of the line between these 2 points, 3,6 and 6,5. From 3,6, we go down 1 unit and across to the right 3 units. That's a gradient of negative 1 divided by 3. That's the same as what we worked out algebraically. And since all of the lines are parallel, they all have a gradient of negative 1/3. Now let's make sense of the y-intercept. We worked out that the y-intercept is at c divided by 30, but we don't know where that is on the graph. Let's look at this line. It cuts the y-axis at 7, so it has a y-intercept of 7. So for this line, c divided by 30 must equal 7. If I multiply both sides by 30, I get c equals 210. That makes sense because that's exactly what we worked out using the points on the line. We found the cost was 210 at all these points on the line. So we've confirmed algebraically what we already found by testing points on the line. Let's look at this again. First, we drew a line through all the solutions that corresponded to a cost value of 210 cents. We worked out that this line has a gradient of negative 1/3. Then we looked at the next cost value, which was 200 cents. When we joined these points, we found the line was parallel to the previous one and cut the y-axis at a smaller value of y. We carried on finding parallel lines until we reached this line at the bottom of the feasible region. The best solution was on this last line because it has the smallest y-intercept. The smallest y-intercept gives you the lowest c value or the lowest cost. These parallel lines are called search lines in linear programming. We can use the equation for cost to draw just one of these lines, and then we can move that line up or down, keeping its gradient the same all the time. Moving this line, I land up here. If I go any lower, there are no points on the line that still fall in the feasible region. But at this point, 6, 2, this line is still within the feasible region. This is the optimal solution for the problem. Now let's see if we can use our new method on a different problem. Let's go back to the developer who wants to put housing units on a piece of land. The developer has 10,000 square meters of land. He wants to divide it into 1,000 square meter stands and 2,000 square meter stands in a way that will give him the best profit. The constraints in the problem are the total land available, the cost of preparing the land to make it ready to sell, and the town planning regulations about how many housing units can be built on the land. This time, to find the best combination of plots, we'll try to find an equation for the amount of profit he can expect. The total profit is made up of the profit from the smaller stands and the profit from the bigger stands. If we use X for the number of smaller stands and the profit on these is expected to be 5,000 Rand, I can say that's 5,000X. If we use Y for the number of bigger stands and the profit on these stands is expected to be 15,000 Rand, that's 15,000Y. To complete the equation, I'll write profit equals 5,000 times X plus 15,000 times Y. To find a straight line for this, it helps to put this into the form Y equals mx plus c. That gives Y equals negative 1/3 times X plus profit divided by 15,000. So we can see that the graph has a gradient of negative 1/3 and it has a y-intercept of the profit P divided by 15,000. So now we can draw a line that passes through the feasible region and has a gradient of negative 1/3. We won't worry about its y-intercept so long as the gradient is right. Let's go from this point 0 and 1. From here, I must go down 1 unit and across to the right 3 units. That takes us to the point 3, 0. So these 2 points are on a line with the right gradient and I can join them. This line goes through 2 possible solutions in the feasible region. This solution at 0, 1 would have a profit of 15,000 Rand. This solution at 3, 0 would have the same profit value of 15,000 Rand. Look at this point 0, 1. It is the y-intercept, so if we look at the equation again, we saw that P divided by 15,000 is the y-intercept. So 1 equals P divided by 15,000. So I get P equals 15,000. Now look at this carefully. If I slide the line up so that it is parallel to this one, I will pass through other solutions in the feasible region. Let's stop here. The y-intercept of this line is greater than the y-intercept of the previous line, so we know the profit will be greater. We can work out what this profit will be in one of 2 ways. We can say that the y-intercept is 2, so that this line 2 must equal P divided by 15,000. So if I multiply both sides by 15,000, I get P equal to 30,000. Or I could note that this line goes through 3 possible solutions at 0, 2, 3, 1, and 6, 0. If we check what profit we get at each of these points, we'll get 30,000 Rand. So as you move the line up, it passes through points in the feasible region. Because the y-intercept is increasing as you move the line up, the profit will also increase. Can you see why we call this line a search line? Now we need to move it until we reach the last possible solution in the feasible region where the line will have the largest y-intercept. We get to this point 4, 3. It represents 4,000 meter squared stands and 3 2,000 meter squared stands. When we work out the profit at this point, we'll get 65,000 Rand. So this is the best solution, the solution with the most profit. If you test every point in the feasible region, you will see that this point, 4, 3, will give the developer the most profit. First, in both problems, we used linear inequalities to plot the feasible region. Then, in the nutritional supplement problem, we calculated the cost at each point in the feasible region and wrote it onto the graph. By testing each point, we found the optimal solution. After that, we worked with the developer's land problem. We used a different way of finding the optimal solution. Instead of testing each point in the feasible region, we set up an equation for the profit. The gradient of this equation gave us a search line. Then we moved this search line across the feasible region until we found the optimal solution. For the problem about nutrition, the optimal solution was the one with the lowest cost. For the housing development problem, the optimal solution was the one with the highest profit. Now for today's task. I want you to do both of these problems again for yourself. Set them out neatly and use the graphs the way we have done in the lesson.